In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic.
All right, hello and welcome everybody to Aether Roundtable number 79. Tonight, Dr. Bennett is going to take us through the Einstein Train Challenge and a couple of other things, followed by a live Q&A after. Dr. Bennett, whenever you're ready, sir.
Okay, thank you, Alan. I'd like to start with the theme song that I used in other presentations. Let me see if I can navigate to it.
Starting us off with a little Caitlin Perry, Dr. B?
Not exactly.
Okay.
Let's see what it is. Katy Perry is still in orbit, isn't she?
She's so down to earth or whatever now.
Liar, liar.
Liar.
Second place. Yeah, baby. Anybody hearing that? I'm not hearing that.
Negative, Ghost Rider.
What's the problem?
When you share full screen, it doesn't share audio, I think. Or maybe you didn't, or maybe you didn't check share audio.
All right. Oh.
Yeah, try resharing your screen and make sure the audio switch is turned on before you. After you hit the entire screen tab and then down right, there's a share audio before you hit the share button.
Okay, so I'm going to stop sharing and start again.
Yeah, so you hit the entire screen tab, and then down to the right, there should be a share audio switch as well.
No. User settings, turn off. Nope. Share screen. But
Yeah, you
no
gotta hit
share.
that.
Is that in the users? Is that in the user settings?
No, it's in the share. It's right in the share screen. When you go to the screen
Right.
and you choose the application, you gotta also choose audio, but only after you select the thing.
Okay. Hmm. Nope, I can't say anything. Share audio.
Well,
So when you hit share your screen button, are you hitting the entire screen tab, or are you on the window tab or the browser tab in the top? Are
I'm
you
on
clicking
both
entire
sides.
screen?
Let me get out of this first. All right. Share.
And then there are options across the top, window and entire screen. I'm guessing the last one is what you're opting for, because I saw your toolbar last time. So after you click entire screen, then on the bottom, there's a little switch button in the bottom right above cancel. And the text for it is in the bottom left, which is about also sharing your audio. And then you punch share and away you go.
Well, it says share server invite link. No.
Well, we should probably just go ahead and get started anyway, because the music's going to get copyright striked out anyway. So we can just
Really?
work.
Wow.
Yeah. Every time, any song ever. So we can just skip it.
Okay. You guys, if you want, that was a a parody of, or a exhibition of the Twisted Sister song, and was done by Nandy Bushell, really a talented young drummer. Go back then to
Yeah, YouTube doesn't like other people's music. There's a dude Anomaly who writes his own music and he gets his own stream struck when he plays his own music. So YouTube is pretty finicky.
Yeah, I play Toby's custom written like tunes at the beginning,
Yeah.
and every time I go live, a different company copyrights it.
That's amazing.
Impressive.
oh, I just found the page where share audio.
Oh, dang.
It's turned on.
Yeah, I don't know. It's weird.
Down at the bottom, it says also share audio.
Yep, that's the stuff. So just make sure the switch is to the right and then go hit share. Let's get her in gear.
Right.
All right. Someone suggested in the chat that Man of Stone just sing it. Stone, give us a little Twisted Sister for the boys.
We're not gonna take it. No, we're gonna take it. We're not gonna take it anymore. How about that? Was that good?
Nailed it.
That's pretty
This is
loud.
up now.
Did I distort?
No, you're
Not loud
set.
enough.
Screw those copyright guys.
All right, share screen. This is what we just had.
And Dee Snider's still kicking. I think he was touring last year, if memory serves.
Sure is.
Hey, it's good to see all the
All
old
right.
school lads, Ken and Brian and Zetetic and he disappeared, Steve.
What's up, y'all?
So about to
All
get
right,
into
we
a
are up the
Dr. B
screen.
Prezi.
It's looking good.
Go back to the Word document. We're good.
You're good. Yeah, we could hear you. You're
Yeah,
solid.
everything's up there. Bug over to the Prezi.
Nailed it.
You got her.
No, we're not going
All
to.
right.
Dang, Stone, you got me all amped up now.
All right. Are we back to special relativity?
Yes, sir.
All
Yes,
right.
indeed.
And this was supposed to motivate everyone, because what we're going to discuss is how Einstein has faked it for 120 years. Yeah, since 1905.
So feel free to hit the hide tag on that bottom button on the right side. It's covering up some of what you're doing.
Okay. You guys got to speak up, because I'm assuming whatever's on my screen is what you're seeing.
Yep, you're good now.
Okay, I'm going to be covering the book that you see, the book cover on the left, which is more or less the Bible of special relativity. Einstein was asked by the demands of the public to write a book that would be readable by the general public. And so in 1916, which is shortly after publishing General Relativity, he started publishing documents, papers. They were eventually collected into a book around 1920. And then final version is in 1930, where he made some fine changes. But basically, the book covers a version written by Einstein himself, which is supposed to cover what the general public should be able to understand for both special and general relativity. I'm only going to cover special relativity. The amount of pages in the book is 90, much too many to try and cover in detail. Wondering, that image on the right, that bug that's on his head, is supposedly the brain virus of special relativity, which he used to infect the rest of the world. It's interesting that in his 1905 paper, the first scientific technical paper that he published on the subject, he divided it into kinematics and electrodynamics. Not dynamics in the sense of mechanics plus E&M, but just electrodynamics. So he seems to exclude mechanics, because mechanics is where you get the most problems when you try to apply special relativity. It's also notable that he did understand the difference between kinematics and dynamics, because he made it the two main sections of his 1905 paper. But as we start reading, we'll see that he violates many of the distinctions that have to be made between kinematics and dynamics. Kinematics is measurement of some physical system, and dynamics is the prediction of those measurements using the laws of physics, like Newton's laws and Maxwell's laws and so on. So we will be keen to separate kinematics and dynamics. because Big Al didn't cover any of the mechanical components of dynamics. All of the illustrations he gives in most of his papers relates to electrodynamics. Now, the alpha model establishes that there is only one frame of reference in which the laws of physics are valid, and that's the lab frame. That totally violates special relativity, and instead of starting into the book and eventually having to stop and point out the conflict between Newton's bucket result and what Einstein is preaching as special relativity, instead of doing that, I'm going to start with a definition of what the alpha model is. So then when I go through the book, I can just refer you back to what we discussed here at the beginning. Now, Newton's bucket, of course, predates Einstein by, well, it was 1687 when it was published. He showed that the laws of physics are true in the lab frame, but they are false in a non-lab frame like the bucket. So if any reference frame is moving with respect to the lab, you cannot apply the laws of physics. And that's it. That's what Newton's bucket is. I presented this before, so let me go through it quickly. In the upper left, you have water stationary in the lab frame. If Newton turns the bucket and causes it to spin, then we have centrifugal forces in effect, which cause the water in the bucket to form a parabola, actually. And the prediction using Newton's law is exactly that. Newton's law says the centripetal force in the upper right is equal to mv squared over r. Well, we have, according to the measurements of Newton in the lab frame, we have a mass, water, we have a speed of rotation, and we have an r, a distance that the water is from the axis of rotation. So he predicts that there is a centripetal force, and that checks with what is measured. So kinematics and dynamics are in agreement. In the bottom row, we have the bucket frame. If you're on the bucket, attached firmly to it, and as an observer, you're watching the water, you see that when Einstein spins the bucket, it looks like not Einstein. It looks like Newton is rotating in the lab around because the bucket observer thinks that his reference frame, the bucket, is at rest. So if Newton saw the bucket rotating counterclockwise, then the bucket observer would see it Newton rotating clockwise. In any event, he sees the same motion that Newton sees, a parabola being formed, but it seems to be formed because the lab is rotating, not because the bucket is rotating. In his frame of reference, the bucket is stationary. So if he applies the centripetal force law with the water being stationary, even though it's forming a parabola, it's stationary, not rotating, he predicts that the centripetal force is 0. And this is wrong because that would predict that the water surface is flat. So for rotating objects, we can say that you must use the lab frame. Some people say this is only because of the rotation that you're getting this effect. If you were using linear motion, you would get a different result. Well, I showed in an example called the hitchhiker, that if you look at the lab frame, which is shown on the left, a hitchhiker observes a car accelerating towards him. So the acceleration is a measurement. We predict that Newton's second law should be in effect because we have a mass and an acceleration. So if we ask, what is the acceleration that the driver feels as measured by the hitchhiker? Then we apply Newton's law, which is F d equals md times a. This is the mass of the driver times the acceleration, and that predicts a force. Now, if you had a spring, you could measure this, but we know that when you accelerate in a car, you can feel the back of the seat press against your back. And if you stop, that is, you decelerate, you know that there is a force that throws you towards the front of the car. So the driver feels an inertial force, and if we did the measurement, we would confirm that Newton's law is valid in the lab frame. Okay? Now, pretend you're the driver and you're observing the hiker. If the car is accelerating towards the hiker, let's say going south, and if you're in the car, you see the hiker accelerating north with the same value of acceleration, because that's the law of relative motion. So we apply Newton's second law. We use the mass of the hiker, mh. We use minus a because this is the opposite direction to the acceleration of the car. And we predict that the force on the hiker should not be zero. In other words, the hiker should feel the same acceleration force, or due to acceleration, that the driver does, but we know the hiker feels no force. Driver feels force, hiker doesn't. Another example that where the lab frame is the only frame in which correct predictions are made. This prediction was made in the lab frame. This was the view of the hiker with respect to the car. This is the view of the car with respect to the hiker. So for both rotation and translation, the lab frame is the only inertial frame. We'll call that the absolute lab frame, the ALF part of alpha. I don't know if you've this, but you can prove that the law of relative motion is a truism. That is, it's absolutely true, independent of physical measurement. Like 2 + 2 = 4 is true, absolutely true. Relative motion is also absolutely true. Okay, let's have a motion vector, call it x, and it can represent a displacement, a velocity, an acceleration, or a jolt, which is a higher level acceleration. All motion variables. These are all distances or distances with respect to time. Let's start with a simple identity. XA minus XB. So we have a vector A and a vector B. And they're equal. We set it equal to each. We set it's the vector difference equal to itself, the identity. Then we factor out a minus sign, so we have a minus XB minus XA. We can abbreviate that to XA comma B, so this is a definition of what that means. And again, if we factor out a minus sign, we get minus XB minus A. If we then let x equal a displacement, a velocity, or an acceleration, etc., then this is always true. It is always true that if you measure the motion of an object, the object measures the opposite motion for you. And that's a word version of what the relative motion formula is. Okay, Einstein says the work that he is presenting, that is the book, requires an education corresponding to a university matriculation exam. In other words, a college level education, and a fair amount of patience and will on the part of the reader. He then says at the end, may the book bring someone a few happy hours of suggestive thought. Well, that's certainly true for me, but most of my thoughts have been negative rather than positive. And that's what I'm going to try and elaborate on in the time that remains. All right, let's start with definitions. Einstein tends not to define anything, especially when he gets to definition of laws of relativity. He has a section called physical meaning of geometry. And one of the definitions are separation of mechanics and electromagnetism. What he doesn't state, and many books don't do this, in order to discuss mechanics, you have to assume that the masses that you're dealing with are neutral, they're uncharged. Otherwise, you'll have forces of electromagnetic nature, and that means that you will have to combine electrodynamics with mechanics. So in all of the things that we say from now on, we're going to assume all of the masses are neutral, uncharged, and so we don't have to deal with electrodynamics. Although we could do that in a different presentation. Now, what is the special relativity postulate? Well, number one says it's the principle of relativity, and he calls it in the restricted sense. If you have two reference frames, K and K prime, and they are in uniform translation, meaning they are moving in a straight line at constant speed, then natural events occur in K prime with exactly the same general laws as in K. So he's saying basically that if you're in this special type of coordinate system, the laws of physics are valid. That's what he's saying. Now, he doesn't say what general laws are valid. What he means is the law of inertia, which is Newton's second law. A body removed sufficiently far from other bodies continues in a state of rest or uniform translation. So that's his definition of inertia. It's also the first law of Newton. His second postulate, which is probably the most controversial, is the law of propagation of light. The light speed in a vacuum travels at a speed c. So if you have a wave and you ask what is the properties or the description of that wave, of the wave speed, well, you have to know what the medium type is. For sound, you'd have to know, is the sound being propagated in air, in water, or what the media is. So the media type has to be known in order to calculate wave speed for material substance. Sound, you also need to know the temperature and the pressure. And if we compare that with postulate 2, which says that the light speed in vacuum is always equal to c, then he is saying that not only is there no effect of the medium, there is no medium at all. In other words, there is no ether, which was proposed to explain how light could propagate in empty space. So instead of water or air, he's saying that nothing exists in outer space. And philosophically, of course, that's not possible. There were nothing in outer space, everything would be connected. If there's nothing between us and the moon, then the moon is right next to us. And of course, temperature and pressure also do not affect light speed. He does admit that ether is possible in general relativity, but we're not covering that. And we'll see that he really doesn't consider ether the way we do. He considers it in a mathematical sense as distorting space and time. Okay, the next definition, Galilean system of coordinates. Coordinates whose motion is such that the law of inertia holds relative to it. Okay, I told you what the law of inertia is. Newton's first law. Einstein says the mechanical laws of Galileo Newton are only valid in a Galilean coordinate system, and we'll define what that is later. SR is the abbreviation for special relativity. Mechanics I described above. It's a branch, kinematics is a mechanics branch that covers the measurements and the mathematical modeling using any motion variables like time, distance, velocity, acceleration. Dynamics is a branch of mechanics that covers predictions based on energy-based theory. So if we used what is called Lagrangian methodology, we can derive the laws of physics and we can identify what are the laws of physics that come under dynamics. So basically, if you were studying physics and you were deciding which branch to go into, you would be classified as either an experimentalist or a theorist. An experimentalist basically applies kinematics, performs measurements in order to discover new theories. A theorist applies dynamics using existing laws to predict future motion. So the difference in kinematics obviously is in making measurements, you're doing it in the present. When you apply dynamics, you're predicting what would be measured in the future. And what we've learned from Newton's bucket is if you're applying dynamics, you have to be in the lab frame. Okay, K and K prime will represent in the future any two inertial frames, any ones that obey the laws we just discussed. If the notation K0 and K, then K0 will refer to an absolute reference or inertial frame, like the lab frame, and K is not. So this notation enables me to separate what is a lab frame from what is not. We'll discuss the train as an example, and the track frame will be identified as the lab frame, and so we would use the notation K0. K0 is the lab frame. All right, Einstein says the book that we're covering is intended to give an exact insight into the theory of relativity. So you are supposed to be able to understand relativity based on what I'll be covering in the next few pages. Okay, we already covered readers who are interested in the theory and have a college level education, but are not conversant with the math of theoretical physics. He says, I make no pretense of having withheld from the reader difficulties which are inherent to the subject. Okay, there's plenty of difficulties, as we'll see. Okay, let's look at some of the individual statements that are made in the book before we get to some of the actual meat of the problem. Einstein says the geometry of rigid bodies is to be treated as a branch of physics. Well, that's interesting because what special relativity will prove is that objects which are rigid in one frame of reference of fixed length will change according to what is called length contraction. So right away, we see that the predictions of special relativity, that lengths contract, is in conflict with his prediction of geometry of rigid bodies as being treated as a branch of physics. In mechanics, there's no separation of kinematics and dynamics. That's the problem with special relativity. Special relativity should only be applied to kinematics because I showed you the law of relative motion is an absolute truth. In dynamics, we have only predictions that are based on laws of physics. Einstein says the visible fixed stars are bodies for which the law of inertia is to a high degree of approximation. Okay, we've been covering astronomy in some of the Discord dialogue. What he's saying is, as astronomers look across the sky, they see the motion of the stars, which is actually along an arc of a circle. What he is saying is that the visible star's motion can be approximated by a chord, a straight line between one end of the sky and the other. So if you follow the path of the stars, we all know that they actually travel along an arc of a circle, and they complete that circle in 24 hours minus 4 minutes. And Einstein is saying he's going to take the motion of the stars as an example of the law of inertia, of translation in a straight line. In other words, he's going to say that for the purposes of his discussion, he's taking the distance that a star travels across the sky as being a straight line, even though we know, in fact, that it's an arc of a circle. So the star paths across the sky are actually constant angular velocity along an arc, but approximated as constant linear velocity along a chord. Okay, so what does that mean? Relative to Earth, every fixed star describes a circle of immense radius in an astronomical day, a result opposed to law of inertia. Why? Because the law of inertia requires motion in a straight line. But he's allowing that this difference is part of his approximation for special relativity. Now, to follow the law of inertia, stellar motions must only use reference frames where the fixed stars do not move in a circle. They move along chords. In other words, he's fitting reality, motion of the stars, to fit the Galilean system of coordinates, straight line motion at constant speed. Sense. This is the diagram that he uses and that we'll use in the train challenge, a better version of this. And this is what he uses to explain the motion of the train, which is shown as this line moving at a speed v. Along the track, there are marks A, M, and B. M is the midpoint of that space, and M prime is the middle of the train when it is at the positions A and B. Now, this is his diagram that he's going to use for explaining the application of his special relativity laws to the motion of the train. Now, in the challenge, some people have said my diagram it can't be understood. Well, the opposite of the diagram that I use is this one, because here there is really no opportunity to explain what will happen when the lightning strikes the two points A and B, and the train continues to travel. There is no indication of what the train would look like after the lightning strikes the train. So see that difference when I get to the challenge. Every event which occurs along the tracks, that is, if it happens at A or B, is simultaneous on the tracks. Excuse me. Every event which occurs along the track also takes place somewhere on the train. So A is both a point on the tracks and a point on the train. B is both a point on the track and on the train. As you'll see, when I do this, I'll separate the two and I'll give separate marks for A and B on the train. Now the question is, in the section on simultaneity, Einstein asks, if the two strokes of lightning at A and B are simultaneous, that is, happen at the same time, are they also simultaneous on the train? And that's what he gets into in this next paragraph. And I go into this because it's where most of the confusion about simultaneity occurs. When we say that lightning strokes A and B are simultaneous with the tracks, we mean the rays of light emitted at the places A and B where the lightning occurs, up here, meet each other at the midpoint M of the length AB. So he's saying when you're in the track frame, that in the lab frame, and lightning strikes at A, he's saying that when the light from A reaches M and the light from B reaches M, they both arrive at the same time. So he's saying that if the distances are equal and they travel the same distance in the same time, they're simultaneous. But the events A and B also correspond to A and B on the train. So when the flashes of lightning occur, the train's midpoint M prime up here matches the point M as it moves towards the right with a velocity VT, velocity of train. A guy on the train moves towards the beam of light from B and away from the beam of light from A. So that's this perspective of B seeing the light coming towards him. Okay, the observer will see the beam of light from B earlier than from A. Why? Because the train is moving towards B and away from A. Train observers conclude that the lightning flash B took place earlier than the lightning flash A. So that's Einstein's analysis. All right, this is quoting a book. Train observers conclude lightning flash took place earlier than the lightning flash, at B took place earlier than at A. Events simultaneous in the track frame are not simultaneous in the train frame. In other words, he's saying the guy at B will see the light before A. Every reference frame has its own time. If the reference frame is unknown, so is the time. So he's saying that it's really not part of his theory to predict what the time is in the first statement of the special relativity. He hasn't solved the problem of telling us what is the time, is it simultaneous or not, whether the light beams reach A and B at the same time on the train compared to the simultaneous arrival of the light beams in the track frame. This is again quoting Einstein. If a mass m moves uniformly in a straight line, which is kinematics, with respect to a coordinate system k, then it's also translating uniformly relative to a second coordinate system, k prime. What is k? The track frame. K prime, the train frame. Having a uniform translation with respect to k. Okay, that's a prediction, and therefore a dynamic statement. So you have a beginning statement that the mass is moving in a straight line. So that's a measurement. But now he's also predicted it will be translating in the second coordinate system, the train frame, with respect to k. This is dynamics. He isn't distinguishing the two. Einstein says mechanical laws will hold exactly in both k and k prime. Again, that's dynamics. The principle of relativity in the restricted sense says if k and k prime are uniformly translating, which is kinematics, then they follow the same general laws. Now he's quoting dynamics for natural events. Why is this important? Because we've found, because of Newton's bucket, dynamics doesn't allow any reference frame to be used. Only the lab frame can be used. And obviously, Einstein is not using that in this. In fact, he's not even distinguishing kinematics from dynamics. Okay, onward. The principle of relativity supplies us with the actual motions of the heavenly bodies with wonderful detail. It must apply with great accuracy in mechanics. Okay, we already said that that's an approximation of linear motion for motion which actually is along an arc. So that raises questions with me. What is this principle of relativity when it's already being used and applied to an approximation of a straight line motion? Now, our friend Wikipedia says the principle of relativity is a requirement that the equations describing the laws of physics have the same form in all its frames. That is what we call inertial reference frames. In Einstein's theory, inertial frames are considered admissible, meaning that the laws of physics, including those of electromagnetism and mechanics, are the same in all such frames. So he's making a claim about inertial frames of reference that they are valid in all inertial frames. We know that this is false, again, because only an inertial frame can be used in which the laws of physics are valid, the lab frame. If the principle of relativity in the restricted sense, that is in the sense of constant linear motion, if that doesn't hold, then the Galilean coordinate system will not be equivalent for the description. What does description mean? Kinematics or dynamics or both of natural events? We have an ambiguity again where he's saying he's going to use these for descriptions without saying, are you describing something that's measured, kinematics, or something that's predicted, dynamics? He says we must choose one system, K0, moving with the reference frame, the observer, as absolutely at rest. In other words, he's admitting that you must use a system in which one system is at rest and all other systems are in motion. Now, in a framework system K0, the train would be system K, where more complex laws hold than in K0. Again, this is Einstein, because K is really in motion in frame K0. In other words, he's saying, if you choose one frame to be at absolute at rest, well, it's really not in motion. Magnitude of the train velocity, different results than the K0 or lab frame predictions. That is exactly what occurs. In dynamics, you get different predictions. If you don't use the lab frame, you get the wrong predictions. Whereas if you use the absolute lab frame as your inertial frame, then the dynamic predictions are correct. So there's irony here. In dynamics, the lab predicts the only correct result, and ALF part represents, of course, absolute lab frame, and the A part represents using ether as the ether wind. Okay, he also uses the sun as his absolute reference frame when he uses the examples of solar system motion. This is more irony because he's assuming what he said shouldn't be used, an absolute lab frame, absolute sun frame. And this is based on mainstream belief that we have a heliocentric universe. And this is what underlies all of Einstein's thinking, that we have the sun as the center, playing the role of the Earth. The sun is assumed by mainstream to be the absolute frame, at least for some of them. And the lab frame is only believed by dissidents such as myself, who believe that Newton's bucket proves that the only valid laws of physics can be found in the lab frame or lab frame. Einstein thinks of the Earth like a train that is orbiting the sun at 30 kilometers per second. If the principle of relativity were invalid, the Earth's direction at any time would be included in the laws of nature. Now he says the laws of nature. Now we know he's talking about dynamics. So Al is saying that if the heliocentric model is correct, and the sun is the absolute lab frame, then the prediction based on laws of motion, which are dynamics, in the Earth frame, K frame, should have to be relative to the sun's position. But we can use the Earth K frame or any frame to measure motion. So again, we have a disconnect between reality, where you can measure motion from the Earth, which we do all the time, and the claim that you should be using the sun as the absolute lab frame. Of course, that's impossible because there is no one that could withstand the temperatures on the sun if we ever sent an observer there. All right, according to Einstein, the annual changing measured velocity directions, that is, as the Earth goes around the sun, the velocity direction changes. The Earth cannot be at rest relative to the sun as the absolute frame, K0. Careful observations, again, it's this observations based on measurement or observations that are derived from predictions, from dynamics. As long as he doesn't distinguish these two, ambiguous position of defining things without actually identifying the distinguishing characteristics, whether they're kinematic or dynamic. Observations have never revealed differences in directions in terrestrial space. That is, taking K, the reference frame, which is not an absolute frame, to be the Earth. This is a very powerful argument in favor of the principle of relativity. In other words, he's saying the fact that we can use Earth, even though we think the sun is the center of the universe, shows that relativity is in force, that you can choose any reference frame that you want, and that the laws of inertia will be valid. Now he has a section called the theorem on the addition of velocities in classical mechanics. And he takes an example, a person walking in a train at speed or velocity m in k, while the train moves with velocity t in k0, has a total velocity in k0, that's the train frame, track frame. You add the two vectors together in the track frame. So you add the motion of the man in the train. So say he's walking up the aisle. This is his speed walking up the aisle. And this vector represents the speed of the train as seen by an observer in the lab frame. Okay, he applies the Galilean law of addition, which means you just add the two velocities together. And now he says this is incompatible with the law of propagation of light from the principle of relativity. We do know with precision that the speed of light is the same for all colors. Okay. The Dutch astronomer De Sitter showed that speed of light cannot depend on the source star velocity. And that's true for all waves. The speed of a wave only depends on its medium, not on its the speed of the source, and it doesn't depend on the speed of the observer either, only the speed of the medium. We replaced the speed of the man in the train with a light beam. Okay, so now we're getting towards the actual example in the challenge. Replace the man with a light beam, so you have a speed of light in k, and you still have the speed of the train in k. So the speed of the light in k, according to what the length of the vectors is going to be less than c. Again, this is all from the book. Okay, in fact, my comments are only in red, or when I point them out. The principle of relativity needs that the speed of light in k and its speed equals the speed of light in k0. In other words, he's saying that the speed of light is the same in all inertial frames. Postulate number 2. Else a new speed of light law is needed for k. So he's saying that there is a conflict here between what we see in the way we added the vectors, because it doesn't agree with his principle that the speed of light is always c. Now, Lorentz, in his investigations on E&M, found that the law of constancy of speed of light in vacuum involved using a rigid ether, and there were new transforms that were introduced called Lorentz transforms that sort of, well, they partially agreed with Einstein, but he used an ether and said that the light moves through a rigid ether, and he derived the famous time dilation and Lorentz, not Lorentz, length contractions. And that's what we'll be studying in a few minutes. Einstein says no empirical data has been found which were contradictory to the principle of relativity. Well, just common sense tells you that if we have two vectors then and we add them together and we get the same value as one of them, that is, if we take the speed of light and add in the speed of the train, we still get the speed of light, then I would call that empirical data that is contradictory to relativity. Now, the space-time theoretical research of Minkowski allowed that in reality there is no conflict between relativity and the law of propagation of light. By using these laws, a logically rigid theory could be derived, the special theory of relativity. We're not going to get into space-time because that's part of general relativity. Space-time model. All right, here's the train example. Here's the repetition of the diagram that Einstein used. This is in his books, and I don't think he used that. I think it was added by the author. Anyway, what it represents is the train's motion from A to B. Lightning strikes at 2 points on the tracks, and actually is between the two lightning strikes. So this doesn't agree with the diagram that actually is needed to calculate what happens if the light beams are simultaneous in the train frame. But this does show you the lab frame. An observer is watching the lightning strikes, the motion of the train. And that's what we call the track frame or the lab frame. If there's a passenger on the train, whatever he measures looking out the window, that represents the train frame. So let's look at what Einstein says happens when the train moves lightning a certain distance down the track until the lightning until the light from the lightning bolts comes together inside the train. Okay, here's his test of simultaneity. Measure the line AB along the track with an observer at midpoint M. That's right here. Let M prime be the midpoint of the distance AB. Okay. Track observer perceives two flashes of lightning at the same time. Then they are simultaneous because the distance AM and the distance BM are the same. And if the light arrives from both at the same time, it's simultaneous. What about the train frame? Are the light beams also reaching the same point at the same time? That light requires the same time t, the same clock readings to cover AM as MB in the train frame is the definition of simultaneity. Okay, there it is. Simultaneous in the track frame means the light rays emitted at A and B, where the lightning strikes the track, meet at midpoint M of the track. Okay, we went over that. Events A and B also correspond to positions A, B on the train. I'm going to use different letters for that in order not to confuse what's on the train and what's on the track. When the lightning bolts occur, M prime coincides with the point M, as is shown in the diagram, but moves towards the right with the train's velocity v, shown there. Now in the track frame, a passenger moves towards the light ray from B, okay, moving towards B, while riding ahead of the light ray from A. So A is chasing the train, while B is awaiting the arrival of the train. Now in the track frame, a passenger moves towards the light ray from B, while riding ahead of the light ray from A. The observer will see the light ray from B earlier than from A. Passengers in the train frame must conclude that lightning stroke B took place earlier than stroke at A. Okay, this is the origin of the fusion. If the light beam from B, no, let's take the train. The train is moving towards B, therefore there is a shorter distance that has to be covered. So why doesn't the light arrive at the train or at the midpoint, as it says, from A rather than B? That's what this paragraph is saying. Okay, so his result, again, all of this is Einstein. Events simultaneous in the lab frame are not simultaneous in the train frame. Okay, because of the argument that I just gave. Because B is at a closer point to the train than A when they actually cross. Every reference frame has its own particular time. We've heard that before. Unless we are told the reference frame and event time unless that we are told the reference frame event time has no meaning. The time required for an event in the train frame must not be considered equal in the same event time in the lab. So he's saying that the time in the train frame, little t, must not be considered equal to the same event time in the lab. He's not saying which one is bigger. He's just saying they're not equal. In the section on relativity of conception of distance, distance AB is measured by a ruler on the tracks in the train. If the man in the train walks a distance d in time t in the train frame, then d in the lab is not necessarily also equal to d in the train frame. Again, he's saying because there's a difference in the arrival of the light beam from the front before the arrival of the light beam from the back. Justifiable hypothesis from classical mechanics. So Einstein is saying that what we're going to cover here in 1 and 2 are not justified. Well, let's see if that's true. The time between two events is independent of the reference frame's motion. Well, let's ask, if that weren't true, then we could have events which happen out of sequence. We could have the collision of a train, two trains, let's say, and one observer says, those two trains just collided. Another observer, who is in relative motion, could say, no, that collision didn't happen yet. That's because they don't agree on what a simultaneous event is. If something like a collision or the arrival of a light beam from the back and the front of the train is seen to happen at one time in one frame, but at a different time in another, then you have a situation which is contrary to what we experience. This is the real problem in the understanding of the laws of special relativity as are being applied to this train situation. The second statement is the distance between 2 points of a rigid body is independent of the reference frame's motion. Okay, so you're saying that if you're on the tracks and you measure AB, you'll get AB. If you're on the train and you measure the same distance, you measure AB, you get the same distance. He says the law of propagation of light may be compatible with the principle of relativity. A relation, the Lorentz transformation, exists between the events in both reference frames, such that every light ray has a speed of light c in both train and lab. So he's saying postulate 2, the law of propagation of light, says that speed of light is the same in both frames. Now, to make measurements, he's using coordinate systems. So let's define what that word means. It means he's using a three-dimensional frame, an XYZ system. One frame is fixed, which is where your observer is, and then a second observer in K prime has a similar coordinate system, three-dimensional XYZ, but is moving with respect to that. I want to point out that this is a mathematical system. It's a way of recording what is measured. It has nothing to do with physics. So a coordinate system does nothing. A coordinate system is a way of writing down what the results of measurements are or what the predictions will be. You could think of it as a scaffold. When you put up a scaffold around the building, you're creating a structure which is rectangular. It's Cartesian because the axes are perpendicular. And what do you use the scaffold for? To create the building from the blueprints. Well, the blueprints in our model are the laws of physics, and the actual building is the measurement. So making the blueprints agree with the measurement is what the coordinate system does. And that's what a scaffold does for an architect and a construction crew. Okay, did I cover this? The lab frame, K, yes, an event in K would be fixed in K by the three planes. So Einstein asks, what are the values of a K prime event when the same event values in K are given? So you have these two inertial frames moving, and an event occurs in one, what happens in the other? Well, the transform was known by Lorentz, and it was copied by Einstein. These are the Lorentz transformations. These are the predicted values in the moving frame if these are the measurements in the stationary frame. You'll notice that there are dependence on the speed of light, c squared, and that there's a square root involved. And what you do is if you make the measurements in this system, you measure x, v, and t, and then you will predict what it would be measured in the other frame of reference. Now, what do these equations represent? They represent what happens if you enforce the law of constant velocity, Einstein's second law, the postulate that speed of light is constant. Now, what about Newtonian mechanics, which was used before special relativity, the Galilean transformation? Well, this is much simpler. It doesn't involve the speed of light, so the speed of light doesn't affect the Galilean transformation. All you do is take the relative speed between the two frames, which is v, multiply it by time, and subtract it from the distance that you traveled in the frame you're in, and that will predict what the distance is in the moving frame. One way of looking at it is the Galilean transformation is a Lorentz transformation with the value of c equal to infinity. If you put c equals to infinity, then v squared over c squared is 0. This is 1. V over c squared, when c is infinite, is 0. So you get t prime equals t, which is Galilean. And up here, again, when c is infinite, this v squared over c squared is 0. Square root of 1 is 1. And you get x minus vt, which is the same as Galilean. All right, so if you're retaining the fact that speed of light varies with the speed of the train, then you use the Galilean transformation. If you say that the speed of light is always constant, c, then you use these equations. Now, if you use the speed of light equals c in the Lorentz transformation, as I showed, you get the values in the Galilean transformation. Now, let's apply this to measuring rods and clock that are in motion. The Lorentz transforms prove that a meter stick moving at v parallel to its length is shortened by an amount square root of 1 minus v squared over c squared. This is called 1 over gamma. So this is the Lorentz contraction. It says that the length of an object in a stationary system will seem to contract, or will, when measured, will have the value equal to the original length times this gamma factor. When v is equal to c, as we showed, the square root is 0. But when v is equal to greater than c, the square root becomes imaginary. In other words, there is no real solution. So we live in a real world, so we can only use values in special relativity where the value of light is c. And if there is a medium, which is not a vacuum, the speed can be less than c, but the value of c can never be greater than c. In our ether model, using ether winds, there is no limit to the ether wind. So when we calculate the speed of light in c plus v, which is the Sagnac result, we can get any value. The value actually is unknown for the total speed of light when we include the speed of ether. Again, the speed of ether, the maximum speed of ether has never been obtained, but never been measured. All right, so meter sticks would shrink, but the Galilean transformation would not cause a meter stick to contract. Lengths and time are the same in the Galilean transformation, but they're never the same in the Lorentz transformation.
You know, I just think we keep saying Lorentz transformation like it's a real thing that we should do just because the math works. I think people need to understand if you're actually mathematically Lorentz contracting anything, you're already in make-believe land, right? Like that's never happening to any instrument. That's just what they say to get out of inconvenient measurements. Anyway.
Yeah, if you go back through the history, you'll find that they said, how can we make the speed of light constant, which is what special relativity demands? And they started playing with this, and they said, well, if we have this square root factor, this gamma factor, then if we multiply it by the length, then the length will contract. And if we divide the time by this factor, time will get longer. And that's just what we need in order to make the light beam from both directions, from A and B, reach the midpoint of the train at the same time. In other words, it's looking at reality and figuring out what math will solve this problem. Instead of asking, is this really the problem that I want to solve, where I want to force the speed of light to be constant all the time? Or do I want to consider the possibility that the speed of light may change depending on the speed of the train? Math plays a big role, of course, especially in general relativity, in the development of relativity. Math should be used to create understanding. Instead, math often is used in the application by relativists to confuse, especially when they find they have a victim who doesn't have a math background. So it's easy to say that these are the formulas we should use and everything works out fine. It does, except it's a pure mathematical world that you're talking about, not the real physical world where we can explain how the light beams can reach at the same time, even though they travel at different distances at different speeds. If you allow different speeds for the light beam, then they can reach the center of the train at the same time. Okay, here's an experiment that Einstein brings up, which was covered, I think, by Alan several times. It's a way they originally used to determine the speed of light inside a moving medium. So you have a setup which is basically the Sagnac experiment. You have a light source which splits the light into two half beams, travel around in opposite directions. They come back, and then at the screen, the light beams are combined, and the difference in their path, which it'll cause a phase difference, and that is recorded as a difference in fringes, or the number of wave difference between the two light beams. Now you start off with an empty pipe. So you just measure this and find out what is the fringe shift, if any, when there's nothing but air inside the pipe. Then you put in stationary water, okay? And that'll change it because the speed of light definitely changes by c over n, where n is the index of refraction. Then what you do is move the water at a speed v, so you see that with the arrows, and you see the oppositely moving light beams, the blue and the red, moving clockwise and counterclockwise. Okay, so we have the black lines representing the water speed at v, and then the blue or the red represents the speed of the water, which equals c over n, when v is 0. Okay, so they measure that then, as I said, with stationary water and see what interference fringes are produced. Now the prediction is dynamics, okay? They're going to get a law which predicts what happens based on what they measure. Okay, so this is dynamics, okay? And therefore, according to Einstein, the special relativity velocity addition formula should hold. This is the formula that relativity tells you. We're not going to go through the derivation. V lab means the speed of the light beam in the lab frame. So for capital V, I'm using SOL, speed of light. And what do they get? C over n plus V divided by 1 plus V over Cn. N again is the index of refraction. V is the speed of the water, and we know what C is. Now subtract the speed of light equals C over n. We know that what the speed of light is when the water isn't moving. So we subtract that out. C over n, and that's what I've done right here. Subtracted it out from the speed of the photons, the light, in the lab frame. That's this. So take the speed of the photons in water plus the speed of the water in the lab, rearrange the terms, and you get the speed of the lab minus C over n. All right. That's where I subtract the C over n. You get this, which is the original, minus Cn. You do some algebra, and you come down with this. And if you now consider, in most cases, the speed of the water is much less than the speed of light. So V over C will be much less than 1. So in this denominator, we have V over C. If we take V over C to be very small compared to 1, we can cross it out. And if you do that, you just get the numerator. So finally, what we get is the approximation that when the speed of light is measured in this Fizeau experiment, the speed of the water, V, is multiplied by 1 minus 1 over n squared. Okay, now notice that C over n up here was the speed of light in a stationary water. This is the speed of light when the water is moving. Notice the difference. There's an n in the denominator when the water is stationary. There's an n squared when the water is moving. So the speed of the photon in the lab minus the speed of the water itself when it's stationary, I claim that this is the speed of light due to the ether motion. What's causing the difference in the speed of light? Well, it isn't the water itself, because when it was stationary, we got C over N. So we get this extra term, this, to the motion of the ether. All right, I'm skipping ahead here. See, speed of light is greater than speed of light in water is greater than 0 minus the speed when it's not in water, and that difference must be 0. So the special relativity addition predicts the speed of light in water, or n in general. Well, what I just pointed out to you was I'm claiming that the speed of the photon in the lab is the combination of the light speed in water plus the water speed in ether plus the ether speed in the lab. Okay, and it's the last term, the 1 over n squared, this, that represents the effect that the ether has. Of course, V represents the speed of the water. It also represents the speed of the ether, as we know from Sagnac experiment.
Bennett,
All right, so this is something new. I've never seen. This.
have you seen that Fresnel derived that under the hypothesis that the density of ether in a material medium was the square of its refractive index?
You know that there are different ways of deriving this, Alan.
Oh, really?
And oh yeah, that's why everyone agrees that this is the right formula. The Fizeau experiment.
Yeah, he came up with it in
Because
1818. That's crazy.
Yeah, but what I'm saying is, as far as I know, I'm the first one to say this extra term here is due, well, actually the V over n squared. That's the effect due to the motion of the ether in the water. Right? If you can find someone or somewhere who says, who has identified that the way I just did.
Oh, yeah,
then,
I can.
Okay, I want to know more about it.
Yeah, from
yes,
there's a mention of it in a David Jackson classical electrodynamics book where he talks about Fresnel deriving that in 1818 under the, like basically the velocity addition is going to be due to the effect of the density of ether in a material medium. That's going to be to that tune of the refractive index squared.
Yeah. Special relativity also predicts this result. Okay. But this result here. But what I'm adding is an interpretation. I'm not adding anything new. I'm not saying I discovered anything new. I'm just saying I can identify a term here that to me represents the effect of the ether moving through the water. Because what you had up here was the speed of light in stationary water. So the only thing that changed is this term, this 1 over n squared. And why did it change? Because when you move the water, you move the ether. You drag the ether. Okay. Okay. Yeah, V over n squared is the speed of ether in a medium having refractive index n. Yeah. Okay, relativity will agree with this, but alpha will also predict the same result if I use what I identified as the speed of ether in water. Okay, Einstein says the electrodynamics of Maxwell-Lorentz in no way opposes the theory of relativity. False. Faraday paradox. I think I covered this before, but we'll do it again. You set up a experiment in the lab where you have a conducting disk, copper disk, and a magnet. That's this black disk underneath, and they're driven by a motor underneath, so that you can control the speed of the two disks. You can loosen up the clamp so you can keep one stationary while the other moves. You can tighten both of them so they both rotate at the same speed. And the pickoff here measures the Faraday law prediction of the EMF produced by the motion of charges in a magnetic field. Okay, so we have a magnetic field produced by the black disk, and the moving charges, when this is rotating, will be moving through magnetic field lines, which by prediction is the Faraday induction law. Now there is an anomaly, there's an exception. Okay, if you want, you could call it an error in the Faraday's law, because if you apply it, as Einstein says, using relativity, that is by saying the relative motion between the magnet and the disk is what causes the Faraday effect, then you should be able to predict all of the measured inductive voltages that are produced. Now, you all recognize this as a generator principle, right? A moving charge, moving wires, if you want, in a magnetic field will produce a voltage, and that's the generator principle. The formula is EMF, electromotive force, from Faraday's law, is equal to the charge Q, that's the charge, free charge in the copper, VCM. Okay, what does that mean? That's the speed of the copper disk C relative to the magnet. So Einstein says it's the relative motion of these two that will produce an EMF, assuming you have the magnetic field. Okay, if you don't have the magnetic field, there's no induction. All right, let's see what the experiments show. If the disk spins and the magnet is stationary, then the test shows that they agree, okay? The green check means the test shows that when the disk spins, this formula is correct. Okay, and SR agrees with that because it's the relative motion of the disk with respect to the magnet. What if the magnet spins and the disk doesn't? Then you get no EMF. And the test predicts, however, according to Einstein, the relativity, that if the magnet spins and the conductor, the copper disk, is stationary, then there is a relative velocity, and there should be an induced EMF. The answer, though, from the experiment, and this is a film that you can see on the internet, the answer to this is no. So they do not agree. The test does not agree with special relativity, hence the X. Suppose they both spin. Well, then what is the relative motion between the two if they're both rotating at the same speed? Zero. The test says, however, there is an induced EMF. There's a green check here. Special relativity predicts no. So where I have the two X's, where a magnet spins and the disk doesn't, or where they both spin, both violate Faraday's law. Now, does the absolute lab frame, the alpha model, based on Newton's bucket, does that solve this problem? Yes, it does. Instead of using the speed of the conductor with respect to the magnet, you must use the speed of the conductor with respect to what? The lab frame. We've indicated that Newton's bucket interprets the laws of physics as being only valid in the lab frame. So Faraday's law should not be speed of charge, the conductor, versus the magnet, but the charge versus the lab frame. Okay? If we measure the speed with respect to the lab of the conducting disk, then they will agree. Let's see if we can check that quickly. If we have the magnet spinning and the test shows no, okay, what would the prediction of the alpha model be? Well, if I, instead of M, I use lab, and the magnet spins, then there should be no induced EMF. And that's exactly what we see. Okay, so if we change magnet to lab in this formula, and the magnet spins relative to the lab, then there will be an induced EMF. If they both spin, then again, we have a speed of the conductor relative to the lab, which is non-zero, and we get an induced EMF when they both spin. So the result is, in both cases, that special relativity is incorrect, and the alpha model, using the lab frame as the only inertial frame of reference, predicts, actually, if you go through all of the combinations, there are 8 different things you could do with the magnet, the conductor, and the lab. Those 3 reference frames represent 8 different ways you could move 2 of them relative to each other. Einstein's special relativity predicts correctly 6 of them. Alpha predicts correctly all 8 of them. Einstein, you're wrong. The electrodynamics of Maxwell-Lorentz in no way opposes the theory of relativity. Relativity is incorrect in at least 2 cases of Faraday's law when applied and experimentally tested. The next section of Einstein is on theory of relativity. The general laws of nature are covariant with respect to Lorentz transformations. Well, this is false. I guess we have to define what covariance is, but the claim that the laws of nature are covariant with respect to special relativities, Lorentz transformations, is false because the laws of mechanics are covariant under Galilean transformations using the ether velocity, not the Lorentz transformation. Now, the definition of covariance is that 2 reference frames, let's call them X and X prime, all right, we have 2 reference frames, X and X prime. For a theory, TR, the laws of motion in the reference frame are F of equals equation X. So suppose theory R is relativity, and the laws of motion obey certain laws, F of X equals some equation of X. If you have a different reference frame, like Galilean reference frame, it's used, and you still have the same force law, even though you use the different variables. In other words, the form of the equation is still the same and still correct. So if you can replace x with x prime, and still the laws of physics are the same in the new transformation, like Lorentz transformation, as they were in the old, then this is a covariant. Then F is covariant. That's what it should say is covariant. Now here's a table which shows you this. We have the mechanics laws of Newton, we have the electromagnetic laws of Maxwell, and we have what are called the EM Maxwell-Hertz laws. The Maxwell-Hertz laws include the total derivative of the electric and magnetic fields instead of the partial derivatives, and it includes using an observer and a reference frame instead of just an observer on a reference frame. If it comes down to the observer can be considered to be moving in the ether frame. So the conclusion of using Maxwell-Hertz equations is that it includes the effects of any ether motion, and get into that would be much deeper than we could afford to do now. Well, let's look at this. For the Galilean transformations, the mechanics of Newton are valid. In other words, if you use Newton's laws with a Galilean transformation, you'll be successful. If you apply Galilean transformations to Maxwell's laws, you will not be successful. So the Galilean transformation is not covariant under Maxwell, in a Maxwell theory. They are, however, successful in the Maxwell-Hertz equations. And the Maxwell-Hertz equations were investigated by Thomas Phipps in a book which is very hard to find, Heretical Physics, but he proves that the Maxwell-Hertz equations are covariant, which means that if we add ether to electromagnetic laws of Maxwell, we will have covariance for both mechanics, Newton, and for Maxwell. In other words, for all of the laws of physics that are important in most of the applications today. Now, Einstein says, of course, use the Lorentz transformations. Well, they will work in the Maxwell laws, but they will not work in Newton's laws. So what happens if you use special relativity is, by using the special relativity law that the speed of light is constant, and by using Lorentz transformations, you force the mechanics of Newton to no longer be covariant. In other words, if you switched reference frames, you won't get the right results in your predictions in the new frame. Now notice, if you use the Galilean transformation and the speed of ether, then you will be covariant with Newton's laws, with Maxwell's laws, and the Maxwell-Hertz laws. Actually, these two become the same. Use the speed of ether for the motion of charges and the motion of masses. Okay, remember the Galilean law is that the total speed is the speed relative to the lab plus the speed of the ether with respect to the lab. Okay, here's the difference in Maxwell-Hertz. The partial derivatives become total derivatives. All right, that's these set of equations. The partial become total, and the velocity of the detector with respect to the lab becomes the speed of the ether. If you've ever been to an airport and you've seen these sidewalks or been on them, then you know that your speed in the airport must be the combination of your walking speed plus the speed of the moving sidewalk. You have a vertical version of that, of course, with an elevator. If you're climbing a ladder in an elevator, then your speed with respect to the ground is the speed of the of climbing the ladder plus the speed of the elevator up. And you can mix the two together and get an escalator where you move vertically and horizontally at a constant speed. And if you walk up the escalator, then you have to add the speed of the escalator to your own walking speed. All right, the laws of Max are the ones that are applied when you use the alpha model, which include the ether velocity. They are covariant under Galilean transformations with ether velocity, not Lorentz transformations. So if you ask, what is the nirvana? What is the set of equations that will solve mechanical problems and electromagnetic problems? The answer is use Maxwell's laws, but use a partial derivative and use a total derivative instead of the partial derivative. And for the speed of the detector with respect to the lab frame, use the velocity of ether. So there you have it, the way to convert what is now non-covariant set of equations. Now you would have at this in this row Maxwell equations, covariant, and the mechanics equations covariant if you use the ether model. Now, what are Einstein's claims for special relativity? If the general law of nature did not satisfy covariance, then at least one of the two fundamental assumptions of the theory would have been disproved. Okay, Al, you said it, not I. SR is disproved. A general law of nature does not satisfy this condition. Okay, right up here is where it's not covariant. Classical mechanics requires modification before it could come into line with special theory of relativity. What does he mean by that? Well, in order to use mass in mechanics, in special relativity, what do you have to do? If the mass is moving, you have to use m over square root of 1 minus v squared over c squared. In other words, you have to use gamma times m. In other words, not just time and space are affected by the Lorentz transformation, but mass and energy and angular momentum, all of the basic fundamental variables of physics are need to be modified in order to satisfy the special relativity. But special relativity adds Lorentz transformation to a Galilean transformation theory, that's mechanics up here, and then misinterprets the experiments by saying, oh, the reason that the mass isn't what we expected to measure is because you didn't use the gamma. The real reason the mass changed is that the speed of ether affects the mass. And that comes out when you use the Maxwell-Hertz equations. Einstein says the principle of relativity requires the law of conservation of energy should hold for every Galilean system. A body moving with velocity v has its energy increased by this amount. So it's gamma times E0. Now, what does alpha say about energy? We agree energy equals mc squared. But according to the Sagnac experiment, he found that the speed of light is not c, but c plus v. This is really vector addition. So it's c plus or minus v. So what if we use the Sagnac formula in the energy equation? We get energy equals m times c plus v squared. Factor out the mc squared. You get the 1 minus v over c, quantity squared. And the v and c as vectors, so that when I write c plus v, it's not scalar, but vector addition. So c and v could be parallel, they could be anti-parallel, they could be perpendicular to each other, they could be at any angle with respect to each other. You would have to use the laws of vector addition in order to determine what the speed of light is. But in any case, it looks like the alpha model would predict that the energy is not divided by the 1 minus v squared over c squared of special relativity, but you multiply by 1 plus v over c and square it times the mc squared, which is, of course, the original E0. So that's something that I haven't tested, but intend to do, and look at the experiments in which they measured the energy in particle accelerators and see if this formula can replace this one. And if not, why not? Is there something I'm missing? Something more that has to be changed with mass? This may change when ether fluid, and that may contribute to the energy. In any case, alpha predicts a different value, since the speed of light is c plus speed of ether. The ether kinetic energy I calculate here, doing basically the same thing as up here, and I come up with the mc squared 1 plus 2 speed of ether over c. Again, according to special relativity, the action at a distance at c always takes place at instantaneous action at a distance. This is contrary to quantum mechanical entanglement, which is a principle which says that if two objects are in a certain quantum state and they are separated by a certain distance, the properties of one, when measured, will determine the properties of the other, independent of the distance between them. So we're finding out that there is the possibility of speeds greater than c. And we haven't discussed this, but Atsukovsky and others, including others, have indicated that there is a second light speed for light. A Tesla is the name I'm thinking of. Tesla has a experiment where he transmits electric energy at speeds which are beyond the speed of light, and claims that this is a second speed of light, which is also what Atsukovsky and others have claimed, that there is a speed of light which is much faster than the speed of light, which is hard to imagine because we already know how fast that is. All right, so this claim of special relativity conflicts with what we know of quantum mechanics. Of course, entanglement, I don't think, was known by Einstein. He died in 1955, and of course he wrote this book around the 1920s. So in any event, his statement is not correct. He has a section called Experience and Special Relativity. All facts of experience which support electromagnetic theory also support this theory of relativity. Well, Faraday's anomaly was known to Einstein. It was known since the time of Faraday. And so, as I just showed you, that contradicts this statement that the experiments show that electromagnetic theory supports the theory of relativity. Now, the relative motion of Earth with respect to the fixed stars is found to be in accord with experience. Actually, the HC model is proven false because if we have the Earth as the center of the universe, the only place which is at rest, then the sun cannot possibly also be at rest because we know the Earth and the sun are in relative motion. Okay, we refer to stellar aberration and redshift of the stellar or star spectral lines from a fixed star compared with their position when produced on Earth. This is the Doppler principle. Well, the Aries test of the star aberration has shown, number one, that the Earth was motionless. Okay, he showed that the claim that the light beam aberrated because of the motion of the Earth, that could be shown to be false. And the transverse ether wind caused the aberration. So redshift can be caused by ether emission by the stars, as we saw in Aries' experiment. Einstein claims the experiments in favor of the Maxwell-Lorentz theory favor SR. The experiments aren't cited. In other words, what experiments is he talking about? Nor is there proof that special relativity is favored. What is it favored over what? No other theory than of Maxwell and Lorentz has been able to hold its own when tested by experience. Well, that's false. Maxwell-Hertz with ether motion solves the Faraday anomaly. Another claim, H.A. Lorentz first introduced the hypothesis that the electron form experiences a contraction in the direction of motion due to its motion. Okay, this is length contraction. This hypothesis has been confirmed with great precision in recent years. No way. No test of Lorentz contraction has been positive. I don't know what he's talking about. No one today claims that Lorentz contraction has been proven without assuming either that the Lorentz transformation is correct, which means you're assuming that the changes in space and time occur according to the transformation, or that there is time dilation. This is circular reasoning. He's assuming that you have Lorentz transformations valid, and therefore that the Lorentz contraction has been observed. What you must do is observe Lorentz contraction directly, actually see something shrink when it moves relative to some other object, and show that that motion is predicted by the Lorentz transformation. You can't assume that the Lorentz transformation is correct and use that as the proof. Einstein says for a long time there were attempts to detect the existence of an ether drift at the Earth's surface. Yeah, he's talking about the MMX, the Michelson-Morley experiment. A speed in the ether frame will cause a change between the perpendicular and parallel motion of the light beam. This difference should have been detectable. It gave a negative result. Okay, notice he calls it a negative result, not a null result. That's even stronger than null because it's saying that there was no result, zero. Michelson and Morley actually reported an average of 7 kilometers per second instead of the expected 30 kilometers per second. That is simply a fact. If you go back and read the original papers, they claimed that the average that they measured was not what they expected. It wasn't the 30, but it wasn't 0 either. This was interpreted by the people that followed, the mainstream physicists, as a null result, meaning 0. 7 does not equal 0. Okay? Another condition which isn't fulfilled correctly. All right. Special relativity. There's no special favored coordinate system. No ether drift, nor any test to demonstrate it. My claim, the lab frame is favored for valid predictions of laws of motion via the Newton's bucket test and the hitchhiker and many others. Ether drift has been proven by the MMX, the Michelson-Sanyak, and Ruyan Wang. So there's a whole bunch of experiments that can be used to refute that claim. Light has always been measured with a speed equal to c regardless of the reference frame. Well, the refuting experiments include the MMX itself, Dayton Miller, Sanyak, Ruyan Wang, and the references are given at the bottom of the paper. The problem with all of the tests that claim that c is constant, they use vacuum interferometers, which are incapable of detecting light waves, since the amplitude of the light wave goes to 0 as the air is pumped out of the light path. This was proven by the Russian Demjanov in 1960. In other words, when you send a light beam through the vacuum, the amplitude of the wave becomes vanishingly small. And if that occurs, then there's no way that you can measure the speed of light accurately, because there's no amplitude to detect, to cause a deflection on the interferometers. Once you put something into the path of a light beam, some material index of refraction, then you will get a measurable value for the speed of light. Cartesian coordinates, we already did that. Einstein uses the term body of reference. Actually, he means the object of measurement, or the frame of reference. Frame of reference is what is commonly used to mean the coordinate system that you're using, an observer, a clock, and a ruler. Those are the basic tools that you need to have a frame of reference. To measure motion, you need the clock and the ruler. You need someone to interpret the readings, that's the observer, and you need a frame in order to organize your results, and that's the coordinate system. Okay, this is an experiment that is often claimed to prove special relativity. It's the Muon decay argument. Muons are elementary particles created by cosmic rays in the upper atmosphere at an altitude of about 30,000 feet. That's about jet cruising altitude. That's about 6 miles. At about 0.2% of the speed of light, the muons should reach sea level in 31 microseconds. That is, this would be the time to travel 6 miles if the speed is very close to the speed of light. So 31 microseconds, in other words, to go from the altitude of the cosmic rays down to the ground. But measurements at sea level showed only 2 microseconds are the decay time. So actually 2.2 microseconds is the decay time for the muons, when decaying at the in the lab frame at the Earth's surface. No one has measured the speed, the decay time of the muons when they're at the cosmic ray altitude. But in order to confirm time dilation, you must know what is the time in one frame, the lab, and the time in the cosmic ray frame, which is not known. So what they do is infer that because the muons are detected at a much greater distance from the cosmic ray decay point than expected if they decayed at when they decay at 2.2 microseconds, that the time must have changed and expanded to create a path of 650 meters using 2.2 micros, which was measured in the lab frame, not in the cosmic ray frame. So to compare the time dilation, we need the time in the lab and at the distance h. The decay time is 2.2 microseconds when the height is 0. But and v equals 0, the time is what? At h equals 6 miles. This has never been measured, and it is needed in order to make the claim that there's time dilation occurring here. So what they're doing is assuming that the decay time at the lab level is the same as it is up here at cosmic ray altitudes. To do the experiment right, you would have to measure the decay time of muons as they decay from the cosmic rays. That is at an altitude of 30,000 feet. That's never been done. Now, even Feynman says that he agrees with special relativity, that time can vary from place to place, a difficult concept, but since Einstein used it, and it's correct, believe it or not. Well, it's incorrect, believe it or not. We can explain time dilation using Galilean transformations and an ether wind. Why does special relativity make these errors? Because they focus on abstraction. They get away from the real world, and they get involved in Lorentz transformations and manipulations with math that, if you trace them back to the reality, they have no foundation in reality. The quality of the experiments is lost when you only consider the numbers, and that's a philosophical viewpoint. Okay, one conclusion we can make here is that relativity only applies in kinematics. Whenever you see relativity being applied in dynamics, remember Newton's bucket. Remember that an absolute lab frame is required. Relativity only applies kinematics, and the only inertial frame, only place you can make predictions from is from an Earth observer, a lab frame. Okay, this just shows the difference in usage. In the 1905 paper, Einstein mentioned kinematics 5 times and dynamics once. And he mentioned electrodynamics 16 times. Coordinate, we don't care about that. When it came to 1920, which is 15 years later, he no longer discusses kinematics. He no longer includes dynamics in the 90 pages of his book, but he discusses electrodynamics 4 times. So notice he's ignoring kinematics and dynamics in his special relativity book, and he's even ignoring, to a greater extent, the electrodynamics that he discussed in the original paper. It's interesting to see how just the use of the words indicates the direction that he's taking. He's ignoring kinematics, which is where relativity is supposedly applied. Okay, what I wanted to do is to challenge. And it will be a challenge to find it. Faith. Let's well, let me see. Oh,
Is it the second Word doc down there?
Is it in the PDF you had up?
yeah, I went to the application.
Down on your program bar below you there, just to the left, the red one. Is that the one you're talking about? Down left.
Main chat. What, this?
No, down left on your program bar next to your Word doc. There's a red icon. Straight down from where you are now. Not in this window. Below it.
Oh,
yeah. See the Word doc and to the left there in red?
Totally. All right. It's not it. Oh, wait a minute. Train challenge. All right. Einstein train challenge. You got it?
Yes, sir.
Good call, Alan.
All aboard the Einstein train.
All right. And this is the challenge to believers in mainstream physics. All right. Big Al intended to simplify public knowledge of SR by using his best examples of simultaneity, the train thought experiment. All right. That's what we're going to analyze below. Well, as far as I'm concerned, it's a logical train wreck because it results in a special relativity only applying when nothing moves. So let's take a look at this. Train is moving to the left at V. Okay, so we have the train moving at a speed greater than 0. When two lightning bolts simultaneously strike the tracks at A and B. All right, we've gone over that before. Except that now I'm calling the rear of the train R, the front F, and M prime, which Einstein also has, is the midpoint of the train. So R and A and F and B correspond to lightning strikes. All right, if you want, there's marks on the track at A and B, and there's a mark on the back of the train in the front corresponding to what the lightning bolts produced. They also produce the light that travels from the rear front and from the front towards the rear. So when the train moves down the tracks by a distance from A to R, okay, from A to R, the light from the back strikes something in the middle that indicates that it has arrived. You could imagine that it's a man with tilted mirrors so he can see both light beams coming, which would be a crude way to do it. You could have a photocells, 2 photocells, and an AND gate connected to them so that there is an output only when there are two signals from the photocells at the same time. Or you could have an explosion when the light beams, whatever way you want to do it is not important. There is some way of measuring if the light beams arrive at M prime and it can be done in a technical way, accurately. And the diagram shows that in order for this to happen, the light beam from the rear must travel a greater distance. As you can see, the A to M prime is greater than the distance from B to M prime. That's because the train has moved to the right in the time that it took for the light beams to reach the middle of the car. Okay. Now, if this is incorrect, if this is, as Einstein says, that these two arrows should be the same length, that is, they should both be C, then the math will show that. I'm going to calculate what are the conditions that the light beams reach M prime at the same time. I'm going to do the math, which, by the way, of course, Einstein did not do. And of course, he would claim, well, this was a book written for people who were not familiar with physics. But he did say college level, and that would include college level math. And all I'm going to use is algebra. So I don't see the problem with using math to analyze this situation. He only used words to describe what happens. And what we're going to do is quantify that argument and use math. Now, when I issued the challenge, a few people have said that the diagram they don't understand it. So let me stop now, point out the train is moving in this diagram. When the lightning bolts strike, it is not at rest. And I mark that by V here and V here. The times that it take for the light beam from the rear to reach the middle, call that TR. The light beam to reach from the front, call that TF. So I'm not assuming that the times are equal. All right, I'm not assuming that it's simultaneous. If they are equal, then that will prove that this is simultaneous. So does anyone have questions about the diagram before I go through the math? Okay.
Nope, you're good.
Questions, no. Disagreements, yes.
Okay. You want to take up the disagreement now, or you want to wait until page
We
down
can go
when
through
I
what
finish?
you're doing. By all means, I'd like to see if you changed much. But yeah, we can definitely cover it at the end. I'll just re-upload the videos I responded with before.
All right.
And
Photon analysis when the beams meet. Okay, so M prime is the focus. When do the two red beams meet at M prime? The rear light beam. Okay, that's this one. It travels the distance AM prime. So here, that's from A to M prime, is equal to the distance from A to R, okay, plus the distance from R to B, AM prime, rear, yes, AM prime is equal to AR plus RM prime. All right, I don't think I pointed to the right one. RM prime. All right, what is AR? That's the speed of the train times the time of the light beam from the rear. So it's V times TR. Well, that's equal to AR, which is the speed of light from the rear times the time for the light beam in the rear, minus L2. L2 is the distance that's the distance Rm prime.
I'm sorry.
If we
which
solve for
is
L2,
L?
L is the length of the train. For RF,
Oh, half the length of the train.
AB.
I get you.
Well, it's the middle, right? M
I get it
prime
now.
is the middle. Okay, so you solve for L2, all right? So that's just moving the terms around. For the front light beam, you have Bm prime. Bm prime, that's this little distance here. Well, that's equal to M prime F, which is half the length of the train, minus Bf, which is the rest. In other words, Bf plus Bm prime is equal to the length L2. All right, you solve that for L2, and you get L2 is speed of light from the front plus the speed of the train times the time from the front. Now you have two equations, both equal to L2, so you can equate each one. So this here and this here are equal because they're both equal to L2. If you do algebra and you solve for, well, you can solve for anything, but what we're interested in is the time. How does the time from the rear compare with the speed from the front? Well, if we take the ratio of the rear photon to the front photon, TR over TF, then if this ratio is equal to 1, then the two are equal, and that means the light beams arrive at the same time. So the condition that this be simultaneous is that TR equal TF. Now, if you solve this, you get this equation, or these terms. And we want to apply postulate number 2, which says the speed of light from the rear and the speed of light from the front both equal c. So in the diagram, which showed the length of the vectors being unequal, this condition is saying that they are equal because the speed of light is c. So if we set the two light speeds equal to c, and we set this equation, we get that TR equals TF, that they are equal, and this is equal to, if 1 equal to c plus v over v, the condition is only satisfied if v is equal to 0. So if the speed of light equal to for both, and speed you get time has to be simultaneous. In other words, TR equals TF, which I'm just calling T. The only way to solve this is to equal, if v is equal to 0, then you get c over c, which is 1. So 1 equals 1. But what does that mean? It means the train must be stationary. The only way that this will work is if the light beams leave the front and back of the train and the train is stationary. If there's no relative motion of the frames. So special relativity, in this example, applying the second postulate, says that only in statics, not in kinetics, is special relativity valid. But that's meaningless. If special relativity can't be used for kinetics or dynamics, well, then it has no use in physics. In other words, if you want to use Lorentz transformations, you have to use v equals 0, which means Galilean transformations. And that's exactly what you find. If you assume the speed of light is c in the train test, you get a reduced scope for the special relativity. It only applies to stationary objects. time dilation and length contraction do not apply to objects at rest. So you've had 120 years of fraud, basically, by applying laws, special relativity, that violate the laws of logic, because by applying mathematics, we find that the motion that they predict is impossible unless the train is stationary. So when v is 0, the Lorentz transformation becomes Galilean. And what if we can also say the v is what? The speed of the ether that's being dragged by the train. So we can use the Sagnac result, speed of light is c plus v, apply it to the train, and come up with the result that I just showed you. That with special relativity, the prediction is that the train can't move. But with Galilean transformation, you prove that simultaneity is possible for an object in motion like the train. So no matter how fast the train goes, you must always add the speed of the train to the speed of light if it's coming from the rear. And if it's coming from the front, you must subtract the speed of the train from the speed of light. And that's because the v represents the ether being dragged along by the train. So the ether wind model solves this simultaneity problem, and it destroys special relativity as a credible theory because it predicts that nothing can move, everything is stationary when you try to apply special relativity. And that's what the challenge says. Refute the proof above that special relativity is only valid if v always equals 0. And the reference, what should be from the train experiment, Sagnac, Dufour, Prunier, all 6 of their experiments, and Demjanov, which is available on Vixra, that shows that the speed of light can't be measured in vacuum because the amplitude of the wave becomes close to 0. Too small to measure. Not 0, but too small to measure. Okay, what is the history of the challenge? I think only 2 or 3 people have tried to and I had a coherent objection, and I think it's been out for at least a month. So if there's any questions or before we address Stone, let's cover them now. Any questions on, well, specifically the challenge, since I have that on the screen? Are you ready, Stone?
Yeah, I'm right here for sure. Okay, I just posted the first of those 2 animations I did up before back in the main chat just now, again, to refresh. Anybody who hasn't seen it can watch it. And I just want to deal with what you actually have up on the screen right now, that diagram you have. And then over on the right side, you show the 2 flashes meeting at M prime in the very center of the train as it is still moving to the right towards where the front flash originated. That's what I was attempting to show you.
Whoa. Flashes occur at the front and the back, not just the front.
Oh, yes. They originate at the front and the back, but on the right part of your image, you show them meeting at M prime.
Right.
And what I'm trying to assert is that at any velocity, at any train velocity, anything other than 0, those 2 flashes will never meet at M prime. They will meet at another place. In all of these cases where the train is moving to the right, they will meet progressively farther to the rear of the train, depending on how fast the train is going. So that's why I did this example here at 1/4 the speed of light, or 0.25 c. And I remember in one of your responses, you mentioned in response to that, that light would then be measured on the train at 1.75 c. And I think you meant to say 1.25 and 0.75 respectively. That,
Yeah, yes. Yes, there was a
okay.
mistake. I had 1.75 and it should have been 0.75. Yeah.
Yeah, 0.75 and 1.25 for the opposite direction, right? For when that's the C
Right.
plus
Yeah.
V, C minus V effect right there. I got no problem with that. It's just that when you play this video, I start it back at the beginning, so we're 3 event cycles before the lightning actually strikes at M. And you can see that they meet halfway between M prime and the rear of the train.
Okay, so you're saying you're starting your animation back here before it reaches this point,
Yeah,
right?
yeah, I'm starting it way back so that you get an idea for how fast the train is constantly moving through the scenario relative to how fast the light is moving from both sources from the lab reference frame perspective.
Mhm.
And that I
Well, the
drop,
speed of the train, yeah,
I drop a red line on the graph to represent when the light coming from B, from the front of the train, meets the middle of the train as it is still moving towards B. And then if you continue past 2.0, 2.3, or whatever that was, 2.25, and you get to 3.37, that's where I drop the pink line, and that is where the light from point A hits M prime. And they are at 2 different physical points along the track. They happen at 2 separate times. Even within the train reference, if you're on the train, they will still be happening at 2 different moments in time. And those are the 2 same places that I marked with the pink and red lines on the train, where they would also measure those to be at the time when you meet them.
I'm going to have to see this animation.
Oh, just bug over to the main chat.
Scroll down in the main chat there, you'll see it.
Yeah, it's last thing.
You're on main chat already. You just scroll down on the right.
Yeah, go ahead and punch the big triangle right in the middle of it, and it'll just play it back for you right there.
Yeah. Click, yeah.
No.
Just move your
so
mouse
that's
wheel
the
down.
left
You're
tab. You got to
already
get
in
upward.
it. If you go all the way to the right there, you see the slider bar, the light gray box. There you go. Yep, just drag it down.
Take that all the way down.
Yep. That's a pretty cool thumbnail that somebody made for this. It's awesome.
Yep, slide it all the way to the bottom because I just posted it last. There it is.
I can't pull over any further. All right, I'm just kidding.
All right, how do I get rid of this?
He can go up to the right. You can drag that whole thing just by where you dragged it.
I don't want to stop
grab the top right corner of it.
Oh.
There you go. Now he's a little more out of the way up there
All right.
somewhere.
There you go. Perfect.
Yeah.
Okay.
Eek. Okay, so you need to get over to the left tab again and scroll up to main chat again to get to that.
Let's
Yeah,
see.
take that up. One more line. There it is. Main chat. That's the guy. Okay.
Not going to touch
So
anything.
punch the play button. Punch the play button right on the train in the center of it there. See if we can get it to play.
Well, let's see. You have
It won't stop your stream, I promise.
M prime. When M prime reaches M, the lightning strikes A and B.
That's
Right?
right. Yep.
But A and B are not at R and F. I mean, what does R represent in your diagram?
No, I totally agree that I should have moved R and F with the train. That those are the rear and the front of the train in those directions. Those
Yeah,
are
like-
actually out of
like-
place. I apologize for that. That's incorrect. But it doesn't affect the substance of the video, of the animation. But yes, that's to represent the rear
So
and
we
front
have-
of the train. They're misplaced.
Okay. So when M prime reaches M, and the lightning actually strikes A and B, right?
Yep, that's right. At T0.
At T0, okay. And the train is longer than this diagram indicates, because when that happens, the rear of the train should be at A and the front of the train should be at B. But the diagram doesn't
Well,
represent
this
that.
is what I've done is I've actually separated those values. So ignore my placement of R and F in the diagram and imagine that those are both sitting on top of the train as it moves with M prime, you know? And that the lightning bolts do take place at A and B and are outside the train because the train is short and is centered on M at the moment they flash. I just did that to separate the elements a little more, because then you see which ones are part of the analysis and which ones aren't. But,
Yeah, but if
what we
if
should
A
do here, I got a solution for you. What you can do is take your pop-up screen, that's echoing in the upper right, and drag it down to the lower right, because then you can right-click, or actually click the top right of this video. There's a download arrow right over, brought to you by Man of Stone. Okay, we have to go back there on the left tab again. Yeah, scroll up on the left tab.
wait, I just moved the.
Yeah, I know. It takes you back to this menu.
didn't click any-
because you clicked
Didn't
outside.
click
of it.
anything.
That's weird.
Oh. Oh.
There it is. Okay, now, after you click main chat, there, where it says brought to you by Man of Stone in the top right corner of the animation, there's a download arrow. Yeah, hover over that, click that download arrow, and that'll put it to wherever your download or directory is. And you can play that version instead of the one listed here. It's only like 2 meg or however the size of that file. It's not very big. Yeah, 2 meg and change. So wherever that downloaded to, you can just play it from there, and it won't crash your system here, and everybody can watch you watching it.
Okay. What's the name of the file?
It's called train-stone-01. So actually, if you scroll to the bottom of that list we were just looking at, just scroll to the very bottom of it. I bet it might have just tacked it on the bottom. Or you can go up and you can click date modified a couple times and it'll bring it to the top. Yeah, no, don't hide that. That's what you wanted to look there. Because you did download it, right? I wasn't quite watching.
Well, I hit
Yeah, you clicked that download
download.
arrow. You did that one?
Yeah.
Okay, great. So
but
go
I have
back to that
yeah.
file browser we were just looking at. Yeah, bring the file browser back up and then click the top date modified
No,
over on the right where all the no.
should be
Well,
downloads.
maybe it's in downloads. Okay, sure.
So
Again, then
downloads
click
go.
date modified up at the top. Move to the right and then up to the tab
415.
top where it says date modified.
Yeah, this looks like it. Temp drive upload.
But that's
Folder,
that's your
right?
upload, not your download. No,
Check,
that's upload, not download.
Yeah, go ahead back
Go
to
back to your
downloads.
documents folder.
See the top right, date modified, that column with all the dates. Just tap that. Boom.
Yeah, click that to sort by that. There you go.
It's not in
And
there.
It's not there. So I bet it's in documents. So go to your left tab and click documents instead of downloads. Go back to there. And
It's still
date
being
modified is
sorted.
at the top and
Yeah.
it's not there.
Yeah.
So, well, it's downloaded to somewhere else. You need to figure out where. Is it in your videos folder?
Yeah,
or
it's
did it
probably
go
in
to
videos.
your
Probably in videos.
attachments or, you know?
And then date, yeah.
Not there.
Yikes.
Did things go to your OneDrive up top? To the attachments folder? Or I don't know, man. I don't know your file system.
I don't use this OneDrive, although I'm forced to with Microsoft.
Try down just one from there, if it's in attachments or something.
If it was Google Drive, we could just ask for the last file. But
Here, I got an idea.
Well, it's wherever your web browser is downloading to. That's where it went.
Google.
You use a web browser Discord, Dr. Bennett?
Yeah.
Yeah. Okay,
I don't use the app.
Go back to Google. Go back to the Google screen. Just pop that open. Go to the top 3 dots on the right. All the way in the right corner. Yeah.
This?
Yep.
Or this?
The 3 dots. And then go ahead and click downloads. See if it pops up there.
Sure. Good one, Pete.
Is it a
No,
PDF?
maybe you better
Hey.
punch that arrow again. No, it's an AVI.
Oh yeah, you maybe not
It's an
have clicked
MP4.
it.
Yo, lads.
kind of
Punch
file?
that
Would
thing
it
again.
would it
To
be
make
all
sure
right
you
if I
make
just
that.
started a screen share and we joined that real quick and took a gandy at the video?
Sure. Yeah, go ahead. So yeah, you might as well stop sharing doc and check out Alan's screen share instead.
No, Alan, it wouldn't be okay to expedite this and make good time.
All right, lads. Let me know when you're in.
Right.
All right, we're in.
You want me to what?
No, we're still waiting. Yeah, stop your sharing
Unshare?
and then you can see everybody. Yeah, you can see everybody in the voice chat. You want to
Yeah, just hit stop streaming and then scroll down on the left until you see Alan's stream.
just click main voice and then click Alan's icon in the main part. I'm there.
Oh, let me see if I can. No.
In the left tab, it's clicking Mount Wilson, and then all of us icons will pop up on the right, and you just click Alan to watch his live from there. How you doing there?
All right, gentlemen. Where are we at?
Well,
He's
I'm
in.
in. I'm just waiting for the doc to catch
He's
up.
in. He's in. Let's
Does-
go.
Nice.
can-
He's
Yeah,
in.
Here?
Okay, cool.
At the screen, yeah.
Okay, you're watching Alan's feed? Okay, great. Let her play from -3, T-3. Okay, so this is every half of an event moment going by. Just to give you a feel for the velocity of the train for the whole action. That's about how fast it's going to be going. So there's the flash at T0. And now we're seeing the speed of light from each source. And then stop it in the next frame. There it is, 2.0. See that
This one?
at 2.0, that is where exactly where B meets M prime. And A has yet to get there. Okay, so let it go maybe 2 more frames, I think. Yeah. Okay, well, actually stopping there would have been good. Back 1 frame even. Where they meet at M, as you would expect them to, from the lab frame. And I've dropped the red line on the tracks 2 seconds to the right of M. And M prime is still, the blue line is still traveling with M prime. And the light source, the flash from A, is still yet to catch up to M prime. And the one coming from B is already at the rear of the train. They've already met each other, but not at M prime, if you know what I mean. So let it go 1 more frame, Alan. From 3 to 3.25 almost. 1 more frame to 3.3. There you go.
How's that?
3.37. That's roughly where the one from A finally gets over to M prime. And that's a fair bit after the one from B got to M prime, about 1.37 the event seconds, whatever you want to think of them, time units earlier than that. Do you know what I mean, Doc? That there is no scenario here where the train is moving, where the train V is not 0, where it is moving from either left to right or right to left. There's no velocity that this train can go where both of those are ever going to meet together simultaneously from the perspective inside the train at M prime. You know what I mean? That's in your diagram. That's what you show happening, and it's never going to happen.
Well, what you're showing is the special relativity view. That is, you're showing speed of light from the front and the rear, both equal c. Both the same, at least.
But in the lab frame, that's true, right?
No.
No, if you're in the lab frame and you're assuming the ultimate frame, absolute lab frame, A and B are equal distances apart, you're at M, they're going to be meeting at M in your frame, aren't they?
No, you're using the Galilean transformations. If you're in the lab frame, you see a train moving at V, right? The light signal. So Galilean transformation says the light beam moving in the same direction as the train, it's C plus V added to it. And the one that's coming in the opposite direction, it's C minus V subtracted from it. What this illustration shows is the special relativity view, which says, no, they can't be simultaneous. As you point out, they can't meet at the middle of the train. Travel at the speed of light, unless Einstein says, unless the train shrinks and gets smaller, and the time that they take to travel is longer. Right? That's the difference.
No, I don't think so, because the proportionality isn't evident.
Well, the math shows it. If I take C plus V, and I showed in the math that if you add that to C minus V, the V's cancel out, and that in the rest frame, when the train isn't moving, you would measure C, which is correct. When the train isn't moving, the train is the same as the lab frame.
Well, that's what I'm saying. This animation is showing the propagation of light from the perspective of the lab frame, from the track frame. This is how you drew your...
Yes.
your image,
Yes.
so I'm keeping the same frame. That's why I'm showing that there is no place, there is no velocity this train could ever go where the two flashes would meet at M prime.
I
If the
agree.
train is moving.
I agree. Yes, but the way you're stating it is that both the front and the rear travel at some constant speed. It may not be the speed of light, C, it could be any speed, but at any speed, constant speed, I agree. You can't get the two to meet in the middle of the, if it's moving at V. Reason is
At M
that's
primes.
not that's not the Galilean transformation. For one light beam, you have to add the speed of the train. For the other one, you have to subtract speed. And unless V is 0, then the light speeds can't be the same.
Well, you're talking about the light speeds not being the same in terms of how they're going to measure the speed of light coming from two directions while on the train, and only while on the train. And that's what I was pointing out in saying that, yes, it is going to be C plus V and C minus V as far as what they measure the propagation speeds to be while on the moving train. But that still doesn't mean that these two light flashes are ever going to meet at M prime, even from the perspective of the people on the train. The point is that the people on the train are measuring light coming from B at C plus V. That's the 1.25. And light coming from A, that velocity is going to be C minus V, which is 0.75. And this is what we're seeing the effect of from the lab frame in this animation. We're seeing the actual light propagation is, they're both actually C with respect to the observer frame, the one that we're looking at, the alpha, the track frame, they're both the same. That's why they meet at M.
Oh, you mean the original measurement?
Yeah, that the original measurement on the alpha frame, on the track frame, on the absolute lab frame, the light flash from B is going to come at you at C. The light flash from A is going to come at you at C, because that's the absolute and assumedly stationary frame relative to light that is propagating through from both directions, from both distances being equal away and simultaneously striking at those two distances away. You're going to see exactly what I'm showing here at 3.37, that's going to be the rate of overlap from the perspective of, frankly, from both frames. It's just a question of what you perceive when, but that's going to be where those wavefronts exist moment to moment for both frames.
All right. The passenger on the train sees, or measures, I should say, measures the same thing that someone in the lab frame would measure. So if you had a railroad car, let's see, how could you do that?
No, I don't think they would measure the
measurement.
same thing at all.
Well, they would use the Galilean transformation. Whether you're in the lab frame or on the train, in either case, you use the you're on the train, you use the speed of the tracks, but the speed of the tracks is the minus of the speed of the train from relativity. Galilean transformation works both ways. If you're in the train, you considered yourself at rest, and you consider that the tracks are moving to the left at V. All right, that's relativity. Okay, but it's not special relativity, it's relative motion. Okay, special relativity says that the light speed is always C. Whether you're in the train or in the lab, Galilean transformation says that the light from B to reach the middle will travel at C minus V, and the one from the rear will go at C plus V. That explains why, in either case, the light beams will meet at the middle of the train, even though the middle of the train is no longer in the middle of the tracks. It's moved down. It's moved to the right. Math shows that if you add the two speeds together, speed, you get the speed of light.
I guess we're
Minus
going to
V.
have to agree to disagree on this one, because this is the order in which I see these events occurring, regardless of frame, you know? So, okay, let's just move on then. I think I've made my point fairly clear. It's just a question of, do you agree with the points that I'm making?
Not that the speed of light is c in either frame, which is basically what your point is.
Oh, no, I'm not
Speed
saying
of
that.
light.
No, I'm saying that the speed of light as measured in the train is indeed two different values, c plus v and c minus v, based on approaching the light source or receding away from the light source in the case of point A. That yes, they're going to perceive the speed of light as traveling at 1.25 c coming from the front of the train. That's actually
Okay.
c plus v, right? And they're going to perceive light speed as c minus v when it's coming from the rear of the train, because they're moving away from that source. So they will perceive the net speed of light to be c minus v, and that'll be 0.75 c in this particular scenario here, where the train's moving at 0.25.
Well, if the observer on the train has an interferometer, right? Measure the speed of light. We'll measure what the Galilean transformation predicts. The v that he uses, though, is the speed of the tracks, because he considers himself at rest. The train is now the
Indeed.
reference frame.
That's another problem I actually had with Einstein's conclusion about how the people on the train must necessarily conclude that the flashes took place at different times. I think what's not being considered there is the net effect of the experience of the people on the train, who are, like you say, watching the tracks blow past them to the rear of the train. That they should logically conclude not only do they need to measure the speed of light coming from both directions, but they also need to measure the rate at which the tracks are blasting past them, so that they can themselves, within the train, do their own computation regarding time dilation and understand how fast they are really going. And then that, of course, brings me to the second half of the original response I sent you last month, I guess, or maybe earlier this month or whatever it was, a couple weeks ago, about how people in that train even compute how fast they're going with a d over t calculation, and that there is a convergence point, and I forget what the exact value is. I think it was something just over the 2/3 the speed of light, where your d over t value, from the perspective of you on the train at that speed, would compute to something right at the speed of light. And to go faster than that, or appear to hit, where the tracks are blasting past the train at a d over t rate that you would compute as something in excess of 0.7 c, somehow, because of the change in t, your computation would tell you that you're currently going faster than the speed of light, even though from the lab frame they're only doing 0.7 c. That was, if you remember any of that gibberish I typed out in the second half of those several hundred words I sent you. But yeah, that's the other weird inconsistency and problem I have with Einstein's conclusion about the experience of the people who are on the train with respect to their own speed.
Well, yeah, I disagree with his assumption that in order to get simultaneity, you have to say that the speed of light is constant, but that space and time change dimensions. That's what I object to.
Yeah, It's
Math.
that they're going faster, so time is supposed to be slowing down for them, but their T over D, or their D over T, I keep saying that. It's the D over T calculation, where T is supposed to be getting much smaller than it actually is because of your V, that there is a compounding effect in that, mathematically speaking, which creates this massive conundrum about, are you already going faster than the speed of light when your D over T calculation is telling you that you are, but only from within your own dilated frame, if that makes any sense. That from the lab frame, you're still only doing 0.7 C, but from your computation inside it, as your time is dilated, it appears to you that you're already doing faster than C from the raw computation, which I find to be utter nonsense when you consider the theory on the whole. Again, another reason why we should just toss the whole thing out the window.
Yeah, the Lorentz contractions, or the Lorentz transformations always predict that the speed of light is c. That's what you put into the formulas when you calculate the change in time, and dilation of time means time increases. Okay, so if time dilates, lengths contract, then you have more time to cover a smaller distance. And that explains why the light from the back of the train can reach the middle of the train at the same time that the light from the front of the train gets to the middle of the train, because of the combined effect of time dilation and length contraction. Smaller distance to travel, but a longer time to travel it.
What a delightful chapter full of nonsense. All right, I think we've wrestled this one to the ground.
I would suggest, Stone, that in your animation you run your animation with, like Einstein wants, with the speed of light equals c in both directions, and then use the Galilean transformation for whatever v you pick for the velocity of the train. If the Galilean transformations add up, let's see, they should add up, if you calculate the distance, to 2L, I think. Because if they start at the back, no, the total must be L, yeah. So that would be one way to check. Galilean transformations must indicate that the total distance that the light travels is, no, it's 2L, 2L. I'll have to check that.
Either some L other time, no problem.
It's getting late. Are there any other issues? Anyone?
No, not really. Good presentation, Dr. Bennett.
All right, thank you. It's 11 o'clock, so yeah, it's reasonable to stop here. Thing. If you
I think did we lose you, Cass? Hello?
No, he's still here in spirit.
He's there somewhere. I can see him. He's right there.
He's here in spirit.
Well, Stone, can I ask a question real quick? Well, first of all, I definitely agree with your take on that. I think it'd be easier to. Oh, could you leave that up, Alan?
Before Rick. Yeah,
if you don't mind.
ending of the
Oh, he's
Yep.
he's back. Never mind.
trip with Katy Perry.
What?
The last thing we heard was Katy Perry.
See,
You're breaking up just a bit, Dr. Bennett.
didn't dream, right? Oh,
Last
all
thing
right.
we heard was
Let me
Katy Perry.
just. Can you hear me now?
Yes, sir.
Yeah,
Yep.
there you go.
All right. Just go to YouTube and type in "When Faking Space Goes Horribly Wrong," starring Katy Perry. It shows
Isn't that
the landing.
delightful?
What happened?
Did you see that? They show the capsule in the desert, and Bezos is walking around it, right, getting ready to open it. When the capsule opens, you can see the door open, but then somebody says, "No, no, no, it's too early." So they close the door.
Hello, everyone.
And then Bezos comes, and he's got a special tool to open the door. And he opens this, and this is like 15 seconds after they already opened it. So
Oh,
you wonder,
rip.
What's worse is that special tool was nothing more than a ratchet with a socket end on it. And he applied it to the door and barely even connected with the bolt he was supposed to turn as they opened it from the inside. It was embarrassing how Jeff's absolutely beautiful demonstration about how he has zero skill operating a ratchet.
well, besides that, what else did they lie about? All right, is this the second capsule in the desert? I mean, and it's on film. They can't. Well, they're probably trying to get it
Wow, that's a rip.
canceled, but
I just watched it. It's hilarious.
Shout out to Ben from
All right,
Taboo Conspiracy.
Mm-hmm.
How delightful.
And shout out to Caitlin Perry.
They have permanently destroyed any shred of possibility that Jeff can retain anything to do with legitimacy with this entire Origin program. Like his shot at legitimacy is forever destroyed because of those 30 seconds.
there's also a view where he's running around the capsule and he face plants. He trips on something and falls and
into the dig. The dig underneath it.
Yeah.
There's this kind of a ditch of a crater thing they faked. And he jumped right in there. It was great.
I got something for this.
Yeah, too right.
Fake space.
Fake face. Well, thank you, Dr. Bennett. That was great.
Okay, and you
anything else?
are who?
That's the beast.
Who's the beast?
Yes.
Oh, okay. I'm not used to your name. Or your voice, I mean.
No, that's okay. We've talked
Okay,
before.
it's a wrap, Alan.
Yes, sir. Dude, that was an awesome Prezi. Thank you so much.
Maybe I'll do general relativity.
Oh, please do some GR. That'd be so cool.
And you wanted me to do some, I don't know, assistance with a presentation a couple weeks ago.
Oh yeah, we were gonna do what was it? The Andromeda paradox and some other relativity thing that's, equally as dumb. Your suggestion,
the Andromeda strain.
Yeah, your suggestion was just to do the Einstein train.
Oh.
I was gonna have you collab on that. I forget what the other part of it
Well,
was,
until
but I
it-
was going to do that.
Until it is refuted, I'm sticking with the Einstein train challenge.
Yeah.
I want to do one on CMB too, and do one with Mike on unifying Aether, his model and the Hildegard model. I think there's basis for unity there. Come up with a approved model.
Nice. All right. Well, that concludes Aether Roundtable number 79. Thank you, Cass. Thanks, Stone, for the animations and awesome back and forth with Bennett. We will be doing a community Twitter space on Friday, so tune into that. We'll tap in with the lads on Twitter, see what they're doing. And then Sunday, of course, will be Glowbusters at 3 p.m. Eastern. And then next Tuesday, Shane's going to be doing a presentation on reversing the sky clock and figuring out what's going on with that, where they, basically deciphering the timeline out of the eclipse cycles and going over the chronometer. So that'll be interesting. So tune in for that for Sunday or Tuesday.